Welcome to True Projects. In this video, we are going to explain about the project entitled as Power Theft Detection in Smart Grids using Quantum Machine Learning. So before getting into the video, let me give you the brief description about the project. This project focuses on detecting power theft in smart grids by combining quantum computing with machine learning. It leverages quantum algorithms to process large amount of energy consumption data more efficiently than classical methods. The system can identify unusual patterns in electricity usage that indicates theft, improving accuracy and speed of detection. This approach enhances grid security and reduces financial losses for utility providers. Coming to the abstract explains the problem of electricity theft in modern smart grids, especially at the distribution generation side, where consumers with solar panels may falsely report power generation to gain extra revenue. Existing detection methods mainly focuses on consumer side theft and struggles with complex, high dimensional and imbalanced data. To address these issues, the paper introduced a hybrid quantum deep learning model that integrates quantum variational circuits with data re-uploading circuits. This approach improves learning from noisy and complex data. Experimental results on a smart grid theft dataset shows that the proposed model performs better than traditional machine learning models like LightGBM, LSTM, and XGBoost, achieving higher accuracy and more reliable theft detection. Coming to the existing electricity theft detection systems mainly analyze consumer side smart meter data to detect abnormal electricity usage using traditional machine learning models such as LightGBM, LSTM, and XGBoost. While these methods are effective for basic consumption pattern analysis, they fail to detect fraud occurring at the distribution generation side, where users with photovoltaic panels may manipulate electricity generation reports. Additionally, these models struggle with high dimensional imbalanced and noisy data sets, often leading to inaccurate classifications. As a result, current systems have limited capability in identifying complex theft behaviors, which can cause significant financial losses for electricity providers. Coming to the proposed system or base paper work, the proposed system presents a quantum machine learning based hybrid quantum deep learning model named FHQVC DRC to improve electricity theft detection in smart grids. This model combines a quantum variational circuits with a data re-uploading circuits to effectively handle high dimensional noisy and complex data. Classical features are encoded in QUIPs using angle embedding, enabling efficient parallel quantum processing, while parameterized quantum gates help reduce noise and improve accuracy on NISQ devices. The DRC repeatedly reintroduced input data into the quantum circuits to enhance learning robustness. Experimental evaluation using the smart grid theft detection dataset through a Quizquit framework shows that the proposed system outperforms traditional machine learning models, achieving an accuracy of 87%. Coming to the dataset, the theft detection scheme in smart grid dataset consists of smart meter electricity consumption records collected over time for individual users, each identified by a unique ID. It is designed to support machine learning based electricity theft detection by providing features that represent normal and abnormal energy usage patterns. Each data sample includes consumption related attributes along with a target labeled indicating whether the behavior corresponds to legitimate usage or electricity theft. This dataset is commonly used in smart grid analytics to develop evaluate classification models that help reduce energy losses and improve the reliability of power distribution systems. Coming to the novelty or extinction or enhancement or improvement. The proposed extinction enhances the existing quantum models by incorporating quantum entanglement layers which were not utilized in the base approach. Entanglement enables stronger correlations between QUIPs, allowing faster computational through quantum parallelism and interface. It also improves feature interaction, noise resilience, and classification accuracy while supporting essential aspects of quantum error correction. By leveraging these advanced quantum properties, the extended model can capture more complex patterns in a smart grid data, leading to improved electricity theft detection performance beyond what is achievable with classical and basic quantum methods. Along with that, as an extension, a Flask framework is used to develop a user friendly interface that allows users to provide input data for prediction. The inputs are pre processed and passed to the trained model based on the dataset. The predicted results are then displayed through the web interface, making the system easy to access and usage. Coming to the flow of the work, first we have library imports and setup. This module initialized the working environment by importing required Python libraries for quantum computing, classical machine learning, data preprocessing, and visualization. It also configures settings such as warning suppression to ensure smooth and clean execution of the workflow. Next, dataset loading and visualization. In this stage, the smart grid theft detection dataset is loaded into the system and examined to understand its structure and distribution. Basic statistical analysis and visualizations, such as classic distribution plots, are used to identify data imbalance and gain insights into theft versions, non theft cases. Next, data pre processing. This module prepares the data set for the modeling by removing irrelevant attributes, normalizing feature values, handling class imbalance, and shuffling the data. The processed dataset is then divided into training and testing sets to enable reliable model evaluation. Next, metrics initialization. Here, performance evaluation metrics such as accuracy, precision, recall, and F score are defined. A standardized evaluation function is implemented to consistently access and compare the performance of different models. Next, classical machine learning model. Traditional machine learning models such as XGBoost and LightGBM are trained using the pre-processed training data. Their predictions on the test set serve as baseline results for comparison with the proposed quantum models. Next, proposed quantum deep learning model. This module implements the hybrid quantum deep learning models that combines quantum variational circuits with data re-uploading circuits. Classical features are encoded into qubits, processed through parameterized quantum layers, and iteratively re-uploaded to reduce noise and improve learning accuracy. Next, extinction entanglement enhanced FHQVC DRC. The extended model introduced quantum entanglement layers to strengthen qubit interactions. This enhancement improves parallel computation, feature optimization, and robustness against noise, resulting in improved theft detection performance. And next we have performance evaluation and visualization. In the final analysis stage, the performance of all models is evaluated using predefined metrics. Results are presented through tables and visual charts, enabling clear comparison between classical and quantum approaches. Coming to the front end interface allows users to input smart meter data through a web based form. This data is securely submitted to the backend for processing. Submitted user interface is pre-processed and passed to the trained model. The system performs real-time predictions to identify whether the input indicates normal behavior or electricity theft. The prediction results are displayed on the front end in a user-friendly format, allowing users to easily understand the classification outcome and system decision. Coming to the requirements, we have both hardware requirements and software requirements. Hardware requirements consist of operating systems Windows only, processor i5 and above, RAM 8 GB and above, hard disk 25 GB and above. Software requirements consisting of application framework is Python 3.10.9, primary language is Python, front-end framework is Flask, backend is Jupyter Notebook, database is SQLite 3, technologies which we use to build the front-end are HTML, CSS, JavaScript and Bootstrap 4. To execute the project first, we need to open the code folder which contains the project source code files. This folder is a complete package of your project's code base
containing everything needed to develop, test, and deploy your application or model. Static folder. This folder consists of files related to CSS, JavaScript, and Bootstrap. Templates folder. This folder contains all the HTML pages used in the project. It typically includes files like index.html, about.html, etc., which represents different pages of the website. App.py file. This .py file contains the information related to front-end logic. It could include code written in Python that handles server-side operations such as processing user requests, interacting with the database, and generating dynamic content to be rendered in the HTML templates. These are the model files which contain algorithm information which will be loaded into the project code during the runtime. Notebook.ipynb file. This is a Jupyter Notebook file which contains a combination of code, graphs, and outputs all in one place. It allows users to write and execute the code in individual cells, making it a popular choice for data science. Signup.db file. This file is a database file used to store the user information. Coming to the execution of the project, firstly, copy the path of the code folder from the address bar of the file explorer. Then open command prompt. Use the command cd followed by a space and then paste the copied path. This command is used to change the current directory to the code folder's path. Now compile the app.py file using the command python space app.py in the command prompt. This command will execute the Python script and perform a runtime check for any syntax errors or logical issues. After running the app file, the Flask framework will host the application locally at the default address with the port number of 5000. Copy the local link provided by the framework and paste it in any web browser. I prefer Chrome. The home page of the project should now be displayed in the browser. This is a front-end built using Flask framework. In this page, we have Home button, User Login button, and Get Started button. Firstly, click on Get Started button so that the Create account will be opened, where you need to enter the details and create an account for user authentication like username, full name, mail ID, mobile number, and a strong password. Then click on Sign Up so that all the given details are stored in signup.db and login HTML will be opened, where you need to access the application by entering username and password. Then click on login so that the prediction page has been displayed. In this page, we have power theft prediction button, graphs button, notebook button, and logout button. Firstly, click on power theft prediction button so that the power theft detection form will be opened where you need to upload the CSV file to analyze and detect the power theft patterns. Here we need to upload the file. Then click on upload and analyze so that the input is pre-processed and the output is detected as total records are 9, no theft detected is 5, and theft detected is we have the attenuation required like 4 records. Detailed results are given below. And we also have some recommendations like immediate investigation, data verification, security audit, alert system, pattern analysis, and legal action. We also have precautions and best practices given below. And next, the result information is also given like about this result and important notes. Next, we have upload another file button and data visualization button. When you click on upload another file button, the prediction form will be displayed. Again, you can enter the input and check the output. Now click on graphs button so that the graphical representation of the project will be open. Let us check one by one.
First, we have power theft classification distribution graph. The graph shows the class distribution of electricity consumption data used for theft detection. It indicates that there are 1000 no theft incidents and 800 theft incidents, showing a slightly imbalanced data set. This imbalance highlights the need for robust models that can accurately detect theft despite fewer theft samples. Next, we have accuracy comparison graph. The graph compares the accuracy of classical and quantum based models for electricity theft detection. Traditional models like XGBoost and LightGBM achieves moderate accuracy, with LightGBM performing the lowest. The proposed FHQVC DRC model improves accuracy, while the entanglement enhanced FHQVC DRC achieves the highest accuracy, demonstrating the effectiveness of quantum enhancements. Next, we have precision graph. The graph illustrates the precision performance of different models in detecting electricity theft. Traditional models such as XGBoost and LightGBM show lower precision, with LightGBM having the weakest performance. The proposed FHQVC DRC model improves precision while the entanglement enhanced FHQVC DRC achieves the highest precision, indicating fewer false theft detections. Next, we have recall comparison graph. The graph compares the recall values of different models, showing their ability to correctly identify theft cases. LightGBM has the lowest recall, indicating missed theft detections, while XGBoost performs moderately better. The proposed FHQVC DRC improves recall, and the entanglement enhanced FHQVC DRC achieves the highest recall, demonstrating superior capability in detecting actual theft incidents. Next, we have F1 score graph. The graph presents the F score comparison, which balances both precision and recall across different models. Light GBM shows the lowest overall performance, while XGBoost achieves better balance. The proposed FHQVC DRC further improves the F score, and the entanglement enhanced FHQVC DRC achieves the highest value, indicating the most reliable and consistent theft detection performance. And then click on Logout. So finally, the project demonstrates that quantum machine learning can significantly improve the detection of power theft in smart grids. By analyzing consumption data with quantum algorithms, it achieves faster and more accurate identifications of anomalies compared to classical methods. This approach enhances the security and efficiency of power distribution systems while reducing revenue losses for utility companies. Overall, it highlights the potential of quantum technologies in modern energy management. So, this is all about your project. Thank you.
Thank you for watching video. For more projects please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.